Close your eyes for a moment and think about sound. Think about the last time you heard music, the last time someone whispered your name, the last time thunder rolled across the sky and made your chest vibrate. Sound feels so familiar, so ordinary, so completely understood. But what if I told you that everything you think you know about sound is only half the story? What if I told you that sound, at its deepest level, is not just a wave washing through the air? What if I told you that sound, when you zoom in far enough, when you go deep enough into the quantum world, behaves like a particle? A discrete, countable, individual packet of vibrational energy that scientists have given a name. They call it a phonon. Now I know what you might be thinking. Particles of sound? That sounds like science fiction. That sounds like something from a movie. But this is real. This is established physics. This has been confirmed in laboratories around the world for nearly a century. And yet, almost nobody talks about it. Almost nobody explains it properly. Almost nobody takes you on the full journey from the sound you hear every day all the way down to the quantum packets of vibration that make up the thermal energy of every solid object you have ever touched. Today, we are going on that journey. And I promise you, by the end of this video, you will never think about sound the same way again. You will never think about heat the same way again. You will never look at a solid object, whether it is a diamond ring or a copper wire or the screen of your phone, without knowing that inside it, right now, trillions upon trillions of phonons are being created and destroyed every single second. Dancing through the atomic lattice, carrying energy, carrying information, making superconductivity possible, making your electronics work, making the very concept of temperature meaningful. Let me give you some facts before we dive in. Fact number 1. Phonons are the reason that diamond, which is not a metal, which does not have free electrons roaming around, conducts heat better than almost any metal on Earth. Think about that. We always associate thermal conductivity with metals. But diamond beats them all, and the reason is phonons. Fact number 2. Without phonons, superconductivity would not exist. The phenomenon where certain materials conduct electricity with absolutely zero resistance. The phenomenon that could revolutionize energy transmission and computing. That phenomenon depends entirely on electrons exchanging phonons with each other. Fact number 3. Scientists have recently managed to put a single phonon, a single quantum of sound, into a state of quantum superposition. That means a single unit of sound was in two different states at the same time, just like the famous thought experiment with the cat. Except this is not a thought experiment. This actually happened in a laboratory. Fact number 4. Phonons do not exist in empty space. You cannot have a phonon in a vacuum. Phonons are born from matter. They are born from the collective vibration of atoms arranged in a structure. They are emergent. They arise from togetherness. A single atom alone cannot have a phonon. But a trillion atoms vibrating together, that is where phonons live. Fact number 5. The warmth you feel when you touch a hot cup of coffee, the heat radiating from a stovetop, the temperature of your own body, all of that, in solid materials, is phonons. Heat in a solid is phonons. Temperature is a measure of how many phonons are present and how energetic they are. So here is what we are going to do today. We are going to start from the very beginning. We are going to understand sound from scratch, not the way they taught you in school, but the way physicists actually think about it at the deepest level. Then we are going to zoom into solid materials and see what happens to atoms when sound passes through them. We are going to discover that atoms in a solid are not sitting still. They are vibrating. Always vibrating. And those vibrations have rules. They have patterns. They have frequencies. Then we are going to bring in quantum mechanics. We are going to see why the classical picture breaks down. We are going to watch as the continuous vibrations become discrete, quantized, counted in whole numbers. And that is where the phonon is born. After that, we are going to explore everything phonons do, how they carry heat, how they create electrical resistance, how they enable superconductivity, how they interact with light, how they are being used right now in quantum computing research. And finally, we are going to step back and ask the philosophical question: what does it mean for something to be real? Is a phonon real? It carries real energy. It has real momentum. It has real measurable effects. But it is not made of anything fundamental. It emerges from the collective behavior of atoms. So what is reality really? If you love deep explorations of physics, if you love understanding how the universe actually works beneath the surface, then you are in the right place. Hit that subscribe button right now, because this channel is dedicated to taking you deeper than anyone else will. Leave a comment telling me what blew your mind the most. And let us begin. Let us start with something simple. What is sound? At the most basic level, sound is a disturbance that travels through a medium. When you clap your hands, you push air molecules together. Those compressed molecules push the ones next to them. Those push the ones next to them. And a wave of compression travels outward from your hands in all directions. This wave eventually reaches someone's ear, vibrates their eardrum, and their brain interprets it as sound. Simple enough. Sound is a pressure wave in air. But here is something important that many people overlook. Sound does not only travel through air. Sound travels through water. Sound travels through steel. Sound travels through glass, through wood, through stone, through diamond. In fact, sound travels much faster in solids than it does in air. In air at room temperature, sound travels at about 340 meters per second. In water, it travels at about 1500 meters per second. In steel, it travels at about 6,000 meters per second. In diamond, it travels at about 12,000 meters per second. That is 35 times faster than in air. Why? Why does sound travel so much faster in solids? The answer lies in what is happening at the atomic level. And this is where our story really begins. In air, molecules are far apart. They are moving randomly in all directions. When you create a compression, the information has to travel from one molecule to the next, but the molecules are separated by relatively large distances. They have to physically collide to pass the message along. In a solid, atoms are tightly packed. They are held together by chemical bonds. These bonds act like tiny springs connecting each atom to its neighbors. When one atom moves, it immediately pulls or pushes its neighbors through these spring-like bonds. The information transfer is almost instantaneous because the atoms are directly connected. The stiffer the bonds and the lighter the atoms, the faster sound travels. This is exactly why diamond is the champion of sound speed. Carbon atoms are light, and the covalent bonds between them are extraordinarily stiff. So vibrations zip through diamond faster than through any other natural material. Now, let us zoom in even further. Let us look at a solid material at the atomic level. What do we see? We see atoms arranged in a regular repeating pattern. This pattern is called a crystal lattice. In most solid materials, at least the ones that are crystalline, atoms are not randomly scattered. They sit at specific positions, arranged in a three-dimensional grid. Think of it like a three-dimensional chessboard, except at every intersection point there is an atom. And between every pair of neighboring atoms, there is a chemical bond holding them together. Now here is the crucial thing. These atoms are not sitting perfectly still at their lattice positions. Even at room temperature, every single atom in a crystal is vibrating, jiggling back and forth around its equilibrium position. The higher the temperature, the more violently they vibrate. Even at absolute zero temperature, quantum mechanics tells us they still have a tiny residual vibration called zero-point motion. They can never be perfectly still. The uncertainty principle forbids it. So inside every solid object you have ever touched, there is this constant atomic dance happening. Trillions of atoms, all vibrating, all jiggling, all pushing and pulling on their neighbors through the spring like bonds that connect them. And these vibrations are not random chaos. They organize themselves into patterns. Collective patterns where many atoms move together in a coordinated way. These coordinated patterns of atomic motion are called normal modes of vibration. And understanding these normal modes is the key to understanding phonons. Let me explain normal modes with a simple analogy. Think of a guitar string. When you pluck a guitar string, it can vibrate in many different ways. The simplest way is the fundamental mode, where the whole string swings back and forth as one. Then there is the second harmonic, where the string vibrates in two halves with a stationary point in the middle. Then the third harmonic, with three sections, and so on. Each of these is a normal mode. Each has a specific frequency. The actual vibration of the string at any moment is some combination of all these modes added together. Now extend this idea to 3 dimensions. A crystal lattice is like a 3-dimensional guitar string. Except instead of one string, you have trillions of atoms connected in a 3D grid. And instead of the simple harmonics of a string, you have incredibly complex patterns of coordinated atomic motion. Some patterns involve atoms moving back and forth along the direction the wave travels. These are called longitudinal modes. Some patterns involve atoms moving sideways, perpendicular to the wave direction. These are called transverse modes. In a 3-dimensional crystal, for every wavelength direction, you get 1 longitudinal mode and 2 transverse modes. If your crystal has more than one type of atom per unit cell, you get additional modes called optical modes, where different types of atoms move in opposite directions. We will come back to these later. The mathematical relationship between the frequency of a normal mode and its wavelength is called the dispersion relation. In air, this relationship is simple. Frequency equals speed times the reciprocal of wavelength. It is a straight line. But in a crystal lattice, the dispersion relation is more complex. It curves. It has maximum frequencies beyond which no vibration can exist. It has different branches for longitudinal and transverse modes, for acoustic and optical modes. The dispersion relation contains all the information about how vibrations propagate through a particular crystal. The lowest frequency modes, where atoms move together in sync over long distances, are called acoustic modes. These are the modes that correspond to ordinary sound waves. At long wavelengths, acoustic modes behave exactly like the sound waves we know from everyday experience. They have a linear dispersion relation at low frequencies, meaning frequency is proportional to wave vector, which is equivalent to saying that all long wavelength sound waves travel at the same speed. This speed is what we call the speed of sound in that material. But as the wavelength gets shorter, as you approach the spacing between atoms, the behavior changes. The dispersion relation curves and eventually reaches a maximum frequency. You cannot have acoustic vibrations above this maximum frequency. This is fundamentally different from sound in air, where there is no upper limit to frequency. The higher frequency modes, the optical modes, exist in crystals that have more than one atom per primitive unit cell. In these modes, neighboring atoms of different types move in opposite directions. The name optical comes from the fact that these modes can interact directly with light. An infrared photon can be absorbed by an optical phonon, exciting one quantum of this vibration. We will explore this interaction between phonons and light in great detail later. Now we have a picture of a crystal as this complex vibrating system with many different normal modes, each with its own frequency and spatial pattern. Classically, the energy in each mode can be any value. You can put any amount of energy you want into any normal mode. The amplitude of vibration can be anything. There is no restriction. This is the classical picture. And for a long time, physicists thought this was the complete story. But then, something went wrong. In the early 1900s, physicists tried to calculate the heat capacity of solids using classical physics. Heat capacity is the amount of energy you need to add to a material to raise its temperature by 1 degree. Using the classical equipartition theorem, which says that each degree of freedom gets an equal share of thermal energy, physicists predicted that the heat capacity of any solid should be a constant value, regardless of temperature. This prediction is called the Dulong-Petit law, and at high temperatures, it works perfectly. But at low temperatures, experiments showed that the heat capacity of solids drops dramatically. It does not stay constant. It plunges towards zero as the temperature approaches absolute zero. Classical physics had no explanation for this, none whatsoever. This failure was analogous to another famous failure of classical physics that was happening around the same time: the ultraviolet catastrophe. Classical physics predicted that a hot object should radiate infinite energy at high frequencies. Obviously, that does not happen. Max Planck solved the ultraviolet catastrophe by proposing that electromagnetic energy comes in discrete packets, quanta, with energy proportional to frequency. E equals h times f. This was the birth of quantum mechanics. And it turned out that the same idea, quantization of energy, would solve the heat capacity problem for solids. In 1907, Albert Einstein proposed a model for the heat capacity of solids that used the same principle as Planck's quantum hypothesis. Einstein said, "Let us treat each atom in a solid as a quantum harmonic oscillator." A quantum harmonic oscillator is different from a classical one in a crucial way. Classically, a vibrating object can have any energy. Quantum mechanically, a vibrating object can only have specific discrete energy values. The allowed energies are equally spaced, separated by gaps of size h times f, where his Planck's constant and f is the frequency of vibration. This means the vibrating atom cannot have just any amount of vibrational energy. It can have 0 quanta of vibration, or 1 quantum, or 2, or 3, but not 1.5, not 2.7, whole numbers only. This seemingly small change has enormous consequences at low temperatures. At high temperatures, there is plenty of thermal energy available. And it does not matter that energy comes in discrete chunks, because the chunks are tiny compared to the total thermal energy. The classical result holds. But at low temperatures, when the available thermal energy becomes comparable to or smaller than the size of 1 quantum of vibration, suddenly it becomes very hard to excite even a single quantum. Most of the oscillators remain in their ground state, unable to absorb any energy at all, because there is not enough thermal energy available to provide even 1 full quantum. The heat capacity drops because fewer and fewer oscillators can be thermally activated. Einstein's model was a breakthrough. It correctly predicted that heat capacity decreases at low temperatures. But it was not perfect. It predicted that heat capacity drops exponentially at low temperatures, but experiments showed it drops as the cube of temperature. The T-cubed law. Einstein's model was too simple because it assumed all atoms vibrate at exactly the same frequency. In reality, a crystal has many different vibration frequencies, from very low to very high. In 1912, Peter Debye improved Einstein's model by accounting for the fact that a crystal has a continuous spectrum of vibration frequencies. Debye treated the crystal as an elastic continuum and calculated the density of states, which tells you how many vibration modes exist at each frequency. The key insight was that there is a maximum frequency, now called the Debye cutoff frequency, above which no modes exist. This maximum frequency corresponds to vibrations with wavelengths comparable to the spacing between atoms. You cannot have vibrations with wavelengths shorter than twice the atomic spacing, because there are simply no more atoms to vibrate at shorter scales. Using this improved spectrum of frequencies, Debye calculated the heat capacity and got the famous T-cubed law at low temperatures. His model agreed beautifully with experiments. He also introduced the Debye temperature, which is the temperature corresponding to the maximum phonon frequency through the relation Kb times theta d equals h bar times omega max. Here Kb is Boltzmann's constant, theta d is the Debye temperature, h bar is the reduced Planck constant, and omega max is the maximum angular frequency. The Debye temperature is a characteristic property of each material. For diamond, it is about 2200 Kelvin. For lead, it is only about 105 Kelvin. This means quantum effects become important for diamond even at room temperature, while for lead, you need to cool it significantly before quantum effects on heat capacity become noticeable. And now, we arrive at the key moment. The birth of the phonon. We have established that vibrations in a crystal lattice can be described as normal modes. We have established that the energy in each normal mode is quantized, meaning it can only take values that are integer multiples of h bar times omega, where omega is the angular frequency of that mode. Each quantum of vibrational energy in a particular normal mode is called a phonon. The phonon is born. Let me be very precise about what this means. Consider a specific normal mode of vibration in a crystal. It has a specific frequency omega and a specific spatial pattern. If this mode has zero quanta of energy above the ground state, we say there are 0 phonons in this mode. If it has 1 quantum of energy, we say there is 1 phonon. 2 quanta, 2 phonons, and so on. The number of phonons in a mode can be any non-negative integer, 0, 1, 2, 3, up to infinity in principle. The name phonon comes from the Greek word phone, meaning voice or sound. Just as a photon is a quantum of light, a phonon is a quantum of sound. Just as you cannot have half a photon, you cannot have half a phonon. They come in whole units. This naming beautifully captures the parallel between light and sound at the quantum level. Light is an electromagnetic wave that is quantized into photons. Sound is a mechanical wave that is quantized into phonons. The mathematics is remarkably similar. The physics is deeply parallel. But there is one crucial difference. Photons can exist in empty space. They travel through vacuum at the speed of light. Phonons cannot exist in empty space. They require a material medium. They are creatures of matter. They live inside solids and liquids. They are born from the collective motion of atoms. Without atoms, there are no phonons. This brings us to one of the most important concepts in modern physics, the concept of a quasi-particle. A phonon is called a quasi-particle. It is not a fundamental particle like an electron or a photon. It is not made of quarks. It does not appear in the standard model of particle physics. A phonon is an emergent phenomenon. It emerges from the collective behavior of many atoms vibrating together. No single atom is the phonon. The phonon is the pattern of motion distributed across many atoms. Think of it this way. Imagine a crowd of people doing the wave at a sports stadium. The wave travels around the stadium. It has a speed. It has a direction. It carries energy in a sense. It is a real thing that you can see and measure. But no single person is the wave. Each person just stands up and sits down. The wave is the pattern, the collective behavior, the emergent phenomenon that arises from many individuals acting in a coordinated way. A phonon is like that wave in the stadium. It is real, it carries real energy and real momentum. But it is made not of fundamental stuff, but of coordinated collective motion. The concept of quasiparticles is one of the most powerful ideas in all of condensed matter physics. It allows physicists to take enormously complex systems with trillions of interacting particles, and describe their behavior in terms of much simpler entities. Instead of tracking the motion of every single atom in a crystal, which is utterly impossible for any practical purpose, you track phonons. You count them. You follow their creation, their propagation, their scattering, their destruction. The entire thermal behavior of a crystal can be described in terms of a gas of phonons bouncing around inside it. This is an enormous simplification, and it works brilliantly. Phonons are not the only quasiparticles in physics. There are many others. Magnons are quanta of spin waves in magnetic materials. Plasmons are quanta of electron density oscillations in metals. Polarons are electrons dressed in a cloud of phonons. Excitons are bound pairs of electrons and holes in semiconductors. All of these are emergent phenomena. All of them are incredibly useful for understanding the behavior of real materials. But phonons were among the first quasiparticles to be understood, and they remain among the most important. Now let us understand the properties of phonons in more detail. Every phonon has energy. The energy of a phonon is given by E equals h bar times omega. Here h bar is the reduced Planck constant, approximately 1.05 times 10 to the minus 34 joule seconds. And omega is the angular frequency of the vibration mode. Higher frequency phonons carry more energy. Lower frequency phonons carry less energy. This is exactly analogous to photons, where the energy of a photon is also h bar times omega, which equals h times f. Every phonon also has momentum. Well, almost. Technically, what a phonon has is called crystal momentum, or quasi-momentum. It is given by P equals h bar times k, where k is the wave vector of the vibration mode. The wave vector points in the direction the wave travels, and its magnitude is related to the wavelength by k equals 2 pi divided by lambda. Crystal momentum behaves like regular momentum in most situations. It is conserved in interactions. If two phonons collide and produce a third, the total crystal momentum is conserved, with one important caveat that we will discuss later when we talk about clap processes. But crystal momentum is not exactly the same as true mechanical momentum. True momentum is related to the actual center of mass motion of the entire crystal. When a phonon travels through a crystal, the center of mass of the crystal does not actually move. The atoms jiggle back and forth, but they stay in place on average. So the true mechanical momentum associated with a phonon is zero or negligibly small. What we call phonon momentum is really a bookkeeping device that tracks how the phase of the vibration changes from one atom to the next. It acts like momentum in interactions, it is conserved like momentum, but it is not momentum in the purest Newtonian sense. This subtlety is important, but it does not usually cause problems in practice. The wave vector k of a phonon is restricted to a specific range. It cannot be infinitely large. The maximum magnitude of k corresponds to a wavelength of twice the atomic spacing, which is the shortest possible wavelength in a discrete lattice. You cannot have a wave pattern that changes on a scale smaller than the distance between atoms. because there are simply no atoms in between to carry the pattern. The set of all allowed wave vectors forms a region in K-space called the first Brillouin zone. Every phonon lives inside this zone. If you try to go beyond it, the physics just repeats. A wave vector outside the Brillouin zone is physically identical to one inside it, plus a reciprocal lattice vector. This periodicity is a fundamental property of crystals and plays a crucial role in phonon scattering processes. Now let us talk about the different types of phonons. In a crystal with one atom per primitive unit cell, you get 3 branches of phonons: 1 longitudinal acoustic branch and 2 transverse acoustic branches. In the longitudinal acoustic branch, atoms vibrate along the direction the wave is traveling. Think of it like pushing and pulling a chain of springs along its length. The springs alternately compress and stretch. This is exactly what a sound wave does. Compression and rarefaction along the direction of propagation. In the transverse acoustic branches, atoms vibrate perpendicular to the direction of wave travel. Think of it like wiggling a rope side to side. The wave travels along the rope, but the rope itself moves up and down or left and right. In 3 dimensions, there are 2 independent perpendicular directions, giving 2 transverse branches. Things get more interesting when you have more than 1 atom per primitive unit cell. Suppose you have a crystal with 2 different types of atoms, say sodium and chlorine in table salt. Now, in addition to the 3 acoustic branches, you get 3 optical branches, 1 longitudinal optical and 2 transverse optical branches. In the optical branches, the 2 different atoms in each unit cell move in opposite directions. While one atom moves to the right, the other moves to the left. At long wavelengths, this looks like the 2 sublattices vibrating against each other while the center of mass stays still. Why are they called optical? Because in ionic crystals like sodium chloride, when the positive and negative ions move in opposite directions, they create an oscillating electric dipole. This oscillating dipole can interact directly with the electric field of a light wave. So infrared light can be absorbed or emitted by optical phonons, hence the name optical. Acoustic phonons, by contrast, involve all atoms moving together in the same direction, creating no electric dipole, and therefore not interacting directly with light at the same level. The distinction between acoustic and optical phonons is not just academic, it has real physical consequences. Acoustic phonons are the ones responsible for carrying heat in most materials. They have lower frequencies, longer wavelengths, and higher group velocities at long wavelengths. Optical phonons tend to have very flat dispersion relations, meaning their group velocity is low, meaning they do not carry heat as efficiently. But optical phonons are important for other things, like interacting with light and contributing to dielectric properties. Let us now talk about phonon statistics. This is where things get really interesting from a quantum mechanical perspective. Phonons obey Bose-Einstein statistics. This means they are bosons. What does it mean to be a boson? It means that any number of phonons can occupy the same quantum state simultaneously. There is no exclusion principle for phonons. If you want to put 1,000,000 phonons all in exactly the same mode, with exactly the same frequency and wave vector, you can. This is fundamentally different from electrons, which are fermions and obey the Pauli exclusion principle, which says no 2 electrons can be in the same quantum state. The fact that phonons are bosons has profound consequences. The average number of phonons in a particular mode at temperature T is given by the Bose-Einstein distribution function. N equals 1 divided by the quantity E to the power of h bar omega over kBt minus 1. Let us unpack this formula. At very low temperatures, when kBt is much less than h bar omega, The exponential in the denominator is huge, and the average phonon number is essentially 0. The mode is in its ground state. There are no phonons. As temperature increases, kBt becomes comparable to h bar omega, and the average phonon number starts to grow. At very high temperatures, when kBt is much greater than h bar omega, the formula simplifies to n approximately equals kBt divided by h bar omega, which means the phonon number grows linearly with temperature. In this limit, we recover classical physics. This formula tells us something deep. Phonons are thermal creatures. They are created by thermal energy. At low temperatures, there are very few phonons. As you heat a material up, you are literally creating phonons inside it. And when you cool it down, phonons are being destroyed. They are not conserved. Unlike electrons, whose total number in a material stays fixed, the total number of phonons can change freely. They come into existence when energy is available, and they disappear when energy is removed. They are excitations of the crystal, not permanent residents. At absolute zero temperature, the phonon number is 0 in every mode. But this does not mean the atoms are completely still. Quantum mechanics requires each harmonic oscillator to have a minimum ground state energy of 1/2 h bar omega. This is the 0-point energy. Even at absolute zero, atoms are still vibrating with this residual 0-point motion. But since this is the lowest possible state, with no phonons, we cannot extract this energy by cooling further. It is locked in by the uncertainty principle. Now let us talk about what happens to phonons over time. Phonons do not live forever. They scatter. They interact with each other. They interact with defects in the crystal. They interact with the boundaries of the crystal. They interact with electrons if any are present. And through these interactions, they change direction, change frequency, or get destroyed entirely. The average distance a phonon travels before experiencing a scattering event is called its mean free path, and the average time between scattering events is called its lifetime. Phonon-phonon scattering is perhaps the most fundamental scattering mechanism. Even in a perfect crystal with no defects and no boundaries, phonons will still scatter off each other. This happens because the interatomic potential is not perfectly harmonic. Real bonds between atoms are not perfect springs. They have anharmonic terms, meaning the force is not exactly proportional to displacement. These anharmonic terms create interactions between different phonon modes. Through these interactions, two phonons can collide and create a third phonon. Or one phonon can spontaneously decay into two lower frequency phonons, or three phonons can interact simultaneously. These processes must conserve energy and crystal momentum, which constrains what types of scattering events are allowed. The simplest type of phonon-phonon scattering is the three-phonon process. Two phonons combine to form one, or one splits into two. For this to happen, both energy and crystal momentum must be conserved. There are two subtypes: normal processes, where the total crystal momentum is truly conserved, and umclap processes, where the resulting wave vector falls outside the first Brillouin zone and has to be folded back in by subtracting a reciprocal lattice vector. The distinction is crucial for thermal conductivity, and we will come back to it shortly. Phonon defect scattering happens when a phonon encounters an impurity atom, a vacancy, a dislocation, or any other departure from perfect crystalline order. These defects break the translational symmetry of the lattice and scatter phonons. The scattering rate depends on the size of the defect relative to the phonon wavelength. Short wavelength phonons are scattered more effectively by point defects like impurity atoms. This is analogous to how small particles scatter short wavelength light more than long wavelength light, which is why the sky is blue. Phonon boundary scattering happens when a phonon reaches the physical edge of a crystal. At the boundary, the phonon can be reflected back, or it can be transmitted into the adjacent material, or it can be scattered diffusely. In very small crystals or thin films, boundary scattering becomes the dominant scattering mechanism because phonons reach the boundaries very quickly. This is important in nanotechnology, where devices are so small that the mean free path of phonons becomes comparable to or larger than the device dimensions. Phonon electron scattering is the interaction between phonons and the free electrons in a metal or semiconductor. When an electron absorbs a phonon, it gains both energy and crystal momentum. When an electron emits a phonon, it loses both. This interaction is responsible for electrical resistance in metals at high temperatures, and it is also the mechanism behind superconductivity, as we will discuss in detail later. Now we have a comprehensive picture of phonons, what they are, how they are created, what properties they have, and how they interact with each other and with other entities. Let us now turn to one of the most important things phonons do in the real world: carry heat. When you touch a hot object, heat flows from the hot object into your hand. In a solid, this heat is carried primarily by phonons. Let me paint the picture precisely. Imagine a metal rod. One end is being heated by a flame, and the other end is at room temperature. At the hot end, atoms are vibrating violently. In quantum terms, there is a high density of phonons at the hot end. Many phonons of high frequency and high energy. At the cold end, atoms vibrate less. The phonon density is lower. Energy is lower. Phonons, being mobile entities that travel through the crystal, naturally tend to flow from the region of high concentration to the region of low concentration, from the hot end toward the cold end. As they travel, they carry energy with them. This flow of phonon energy from hot to cold is what we call thermal conduction. It is completely analogous to how gas molecules carry kinetic energy from a hot region to a cold region. In fact, physicists often model phonon heat conduction using the same kinetic theory that describes gas transport. The thermal conductivity of a material due to phonons can be expressed using a beautifully simple formula. Kappa equals 1/3 times C times V times L. Here, kappa is the thermal conductivity, C is the phonon heat capacity per unit volume, V is the average phonon group velocity, and L is the mean free path. This formula makes intuitive sense. The more heat capacity you have, the more energy phonons carry per temperature difference, and the higher the conductivity. The faster phonons travel, the more quickly they transport energy, and the higher the conductivity. The longer the mean free path, the further phonons get before being deflected, and the more effectively they transport energy in a particular direction. Now let us use this formula to understand why diamond has such extraordinary thermal conductivity. Diamond is made entirely of carbon atoms. Carbon is a very light atom, with atomic mass 12. Lighter atoms vibrate at higher frequencies, and phonon velocities are higher. The speed of sound in diamond is about 12,000 meters per second, roughly 18 times faster than in air. The bonds between carbon atoms in diamond are among the strongest bonds in nature, covalent bonds in a tetrahedral arrangement. These strong, stiff bonds further increase the phonon velocities. And diamond crystals can be made with extremely high purity and very few defects, meaning the mean free path of phonons is very long, because there is very little to scatter them. All three factors in the thermal conductivity formula are maximized in diamond: high heat capacity, high velocity, and long mean free path. The result is a thermal conductivity of about 2000 watts per meter per Kelvin at room temperature. For comparison, copper, which is considered an excellent thermal conductor, has a thermal conductivity of about 400 watts per meter per Kelvin. Diamond is 5 times better than copper at conducting heat, and diamond is an electrical insulator with no free electrons. All of its heat conduction is done by phonons alone. This fact has practical applications. Diamond is used as a heat spreader in high-power electronic devices. When a laser diode or a microprocessor generates intense heat in a tiny spot, a diamond substrate can spread that heat outward extremely efficiently, preventing damage. Engineers who design high-power electronics care deeply about phonon physics, even if they do not always think of it in those terms. Let us now understand how thermal conductivity changes with temperature. This is a beautiful story that involves the interplay of different scattering mechanisms. At very low temperatures, very few phonons exist because the thermal energy is too small to excite many of them. The heat capacity is low, and consequently the thermal conductivity is low, even though the mean free path might be very long. As temperature increases, more and more phonons are created. The heat capacity rises. The thermal conductivity increases. But this cannot go on forever. As more and more phonons are created, they start bumping into each other more and more frequently. Phonon-phonon scattering becomes increasingly important. The mean free path starts to decrease. There comes a temperature where the decrease in mean free path overwhelms the increase in heat capacity, and the thermal conductivity starts to drop. So the thermal conductivity of a pure crystal typically shows a peak at some intermediate temperature. Below this peak, it rises with temperature. Above this peak, it falls with temperature. For diamond, this peak occurs at about 80 Kelvin, and the peak thermal conductivity is absolutely staggering. Around 30,000 watts per meter per Kelvin. That is 15 times higher than the already impressive room temperature value. At these low temperatures, there are enough phonons to carry significant heat, but not so many that they constantly scatter off each other. The mean free path at this temperature can be comparable to the physical size of the sample, meaning phonons are traveling from one edge of the crystal to the other without being scattered at all by other phonons. Their only limitation is hitting the physical boundaries of the crystal. This regime is called the ballistic regime, because phonons travel in straight lines like bullets, scattering only at boundaries. Now let us return to the distinction between normal and umclap phonon-phonon scattering processes. This distinction is absolutely central to understanding thermal resistance in crystals. In a normal process, two phonons scatter and produce a third, with the total crystal momentum perfectly conserved within the first Brillouin zone. The crucial thing about normal processes is that they do not create thermal resistance. They redistribute energy among phonon modes, but they do not resist the overall flow of phonons from hot to cold. Think of it by analogy. Imagine a crowd of people all walking in the same direction. If people in the crowd bump into each other but keep the overall momentum of the crowd intact, the crowd as a whole keeps moving forward. There is no net resistance to the overall flow. That is what normal processes do. They reshuffle momentum among individual phonons, but do not reduce the total momentum of the phonon gas flowing from hot to cold. Umclap processes are different. In an umclap process, the total crystal momentum of the incoming phonons is so large that the resulting phonon would have a wave vector outside the first Brillouin zone. When this wave vector is folded back into the zone by subtracting a reciprocal lattice vector, the resulting phonon has crystal momentum in a very different direction from what you would expect. In fact, it can end up moving in nearly the opposite direction from the original phonons. This effectively reverses or randomizes the phonon momentum. It is like a member of the crowd bouncing off a wall and flying back in the opposite direction. This creates real thermal resistance. The word Umklapp is German for flip over, and it was coined by Rudolf Peierls, who was one of the giants of phonon physics. Without Umklapp processes, a perfect crystal would have infinite thermal conductivity because there would be nothing to resist the flow of phonon heat. It is Umklapp scattering alone that gives pure crystals their finite thermal resistance at high temperatures. Here is a beautiful fact about Umklapp processes. They require high momentum phonons. The incoming phonons must have enough crystal momentum that their sum exceeds the Brillouin zone boundary. At low temperatures, most phonons have low momentum because they have long wavelengths. There simply are not enough high momentum phonons available to make Umklapp processes happen frequently. As a result, the rate of Umklapp scattering decreases exponentially as temperature decreases. This exponential freezing out of Umklapp processes is why thermal conductivity can become so enormous at low temperatures in pure crystals. With Umklapp processes effectively shut off and only boundary scattering remaining, phonons can carry heat with extraordinary efficiency. Now let us compare phonon heat conduction with electron heat conduction. In metals, both phonons and electrons can carry heat. Electrons in a metal are free to move throughout the material, and they carry kinetic energy with them. In most metals, electrons are actually the dominant heat carriers. This is related to the Wiedemann-Franz law, which states that in metals, the ratio of thermal conductivity to electrical conductivity is proportional to temperature, with a universal constant of proportionality called the Lorentz number. This law works because both heat and electrical current are carried by the same entities, the free electrons. But in insulators and semiconductors, there are no free electrons available to carry heat. All thermal conduction must be done by phonons. This is why insulators are generally poor thermal conductors. Their phonon systems are the only mechanism available, and in many insulators, phonon transport is not very efficient due to complex crystal structures that scatter phonons effectively. But diamond is the spectacular exception. It is an insulator, yet its phonon transport is so extraordinarily efficient that it beats almost all metals in thermal conductivity. This teaches us that phonon thermal conductivity is not inherently inferior to electronic thermal conductivity. With the right material, the right crystal structure, the right atom mass and bond strength, phonons can be incredible heat carriers. Now let us shift gears and talk about one of the most important interactions in all of solid-state physics: the interaction between phonons and electrons. This is the electron-phonon coupling, and it underlies some of the most technologically important phenomena in physics, including electrical resistance and superconductivity. First, let us understand electrical resistance. When you apply a voltage across a metal wire, electrons begin to flow, creating an electrical current. In a perfect crystal at absolute zero, with no defects and no phonons, electrons would flow without any resistance. Their quantum mechanical wave functions would propagate perfectly through the periodic lattice without any scattering. But in reality, at any finite temperature, the atoms of the lattice are vibrating. Phonons are present. And these phonons disrupt the perfect periodicity of the lattice. When an electron encounters a phonon, it can be scattered. It absorbs the phonon, gaining energy and crystal momentum and changing its direction. Or it emits a phonon, losing energy and crystal momentum. Either way, the electron's direction of travel is randomized. After many such scattering events, the net effect is that electrons cannot maintain a steady drift in one direction. They are constantly being knocked off course by phonons. This resistance to the flow of electrons is what we measure as electrical resistance. The more phonons there are, the more often electrons get scattered, and the higher the resistance. Since the number of phonons increases with temperature, the resistance of metals increases with temperature. This is a very well-known experimental fact. The resistance of a copper wire is higher at 100 degrees than at 20 degrees. And the reason is that at higher temperatures, there are more phonons present to scatter the electrons. At very low temperatures, phonon scattering becomes negligible because there are very few phonons. In this regime, the resistance reaches a residual value determined by scattering from defects and impurities. This residual resistance gives information about the purity of a metal sample. The strength of the electron-phonon interaction varies from material to material. In materials where this coupling is strong, electrons scatter frequently off phonons, and the resistance increases quickly with temperature. In materials where the coupling is weak, electrons are less bothered by phonons. The electron-phonon coupling constant, often denoted by lambda, quantifies this strength. In typical metals, lambda is between about 0.1 and 1.5. A lambda close to 0 means weak coupling. A lambda greater than 1 means very strong coupling. And now we arrive at one of the most beautiful and surprising consequences of phonon physics: superconductivity. In 1911, Heike Kamerlingh-Onnes discovered that when mercury is cooled below 4.2 Kelvin, its electrical resistance drops abruptly to exactly 0. Not just very small. Exactly 0. A current flowing in a superconducting ring will continue forever without losing energy. This was completely baffling. How could resistance just vanish? For 46 years, nobody could explain it. Many of the greatest physicists in the world tried and failed. And then, in 1957, 3 American physicists named John Bardeen, Leon Cooper, and Robert Schrieffer published a theory that explained everything. It is called BCE's theory, after their initials. And at the heart of BCE's theory are phonons. Here is how it works. Picture an electron moving through a crystal lattice. As it passes by the positively charged ions in the lattice, it attracts them very slightly toward itself. The electron is negative, the ions are positive, so there is a slight electromagnetic attraction. The electron passes by quickly, but the ions are heavy and respond slowly. By the time the ions have moved a tiny bit toward where the electron was, the electron has already moved on. But now there is a region of slightly higher positive charge density in the spot the electron just left. This region of higher positive charge can attract a second electron. In quantum language, what has happened is this. The first electron emitted a phonon. It disturbed the lattice, creating a vibration. That phonon then interacted with a second electron, which absorbed it. The net effect is that the 2 electrons have experienced an attractive force mediated by the phonon. The phonon acts like a messenger carrying an attractive interaction between the 2 electrons. Now, normally electrons repel each other because they are both negatively charged. But the phonon-mediated attraction, in certain conditions, can overcome the direct electromagnetic repulsion. This happens when both electrons are near the Fermi surface and they have opposite momenta and opposite spins. When the phonon-mediated attraction wins over the repulsion, the 2 electrons form a bound pair called a Cooper pair. A Cooper pair has very different properties from individual electrons. Most importantly, it is a boson. Each individual electron is a fermion, but a pair of electrons with opposite spins has total spin 0, making it a boson. And bosons, unlike fermions, can all occupy the same quantum state simultaneously. When a material is cooled below its superconducting transition temperature, all the Cooper pairs condense into a single macroscopic quantum state. They all occupy the same quantum mechanical state, described by a single wave function that extends across the entire superconductor. In this condensed state, the Cooper pairs flow coherently, like a single quantum mechanical entity. Scattering an individual electron out of this state would require breaking a Cooper pair, which costs energy. At low enough temperatures, thermal energy is not sufficient to break pairs. Since scattering is suppressed, resistance is zero. Literally, mathematically, measurably zero. The evidence that phonons are responsible for superconductivity in conventional superconductors is overwhelming. The strongest piece of evidence is the isotope effect. If you replace the atoms in a superconductor with heavier isotopes of the same element, the superconducting transition temperature decreases. Specifically, it decreases proportionally to the inverse square root of the isotopic mass. This makes perfect sense if phonons are the glue holding Cooper pairs together. Heavier atoms vibrate at lower frequencies. Lower phonon frequencies mean weaker pairing. Weaker pairing means a lower transition temperature. This isotope effect was one of the key clues that led Bardeen, Cooper, and Schrieffer to their theory. The BC's transition temperature depends on three things: the Debye temperature, the density of electronic states at the Fermi level, and the electron-phonon coupling constant lambda. Materials with higher Debye temperatures, higher electronic densities of states, and stronger electron-phonon coupling have higher superconducting transition temperatures. This is why physicists searching for higher temperature superconductors have often focused on materials with light atoms and strong electron-phonon coupling. In 2015, hydrogen sulfide under enormous pressure was found to superconduct at 203 Kelvin, a record at the time. And in 2020, carbon-sulfur-hydrogen compounds under even higher pressure were reported to superconduct near room temperature. Whether or not all these claims have been confirmed, the theoretical basis is clear. Light atoms mean high phonon frequencies, and high pressure can enhance electron-phonon coupling. Phonons are the key. I should note that not all superconductors are explained by BC's theory and phonon-mediated pairing. The high-temperature cuprate superconductors discovered in 1986 and the iron-based superconductors discovered in 2008 are believed to have a different pairing mechanism, possibly involving spin fluctuations rather than phonons. But conventional superconductors, which include most elemental superconductors and many alloys, are definitively explained by phonon-mediated Cooper pairing. Let us now discuss another beautiful phenomenon that arises from electron-phonon coupling, the polaron. When an electron moves through an ionic crystal, it distorts the lattice around it. The negative electron pulls positive ions toward it and pushes negative ions away. This creates a local distortion, a cloud of phonons surrounding the electron. The electron does not move alone. It moves together with its phonon cloud. This composite entity, the electron plus its phonon cloud, is called a polaron. The polaron is heavier than a bare electron because it has to drag the lattice distortion along with it. The stronger the electron-phonon coupling, the larger and heavier the phonon cloud, and the more difficult it is for the polaron to move. In materials with very strong coupling, the polaron can become essentially trapped, localized in one spot, unable to move freely. This is called a small polaron, and it moves not by continuous motion, but by hopping from one atomic site to the next, when thermal fluctuations give it enough energy. Polarons are important in many technologically relevant materials. In transition metal oxides, in organic semiconductors, in halide perovskites used for solar cells. Polaron effects significantly affect electrical conductivity and optical properties. Understanding polarons means understanding the practical performance of these materials in devices. Now, let us shift to another fascinating realm, the interaction between phonons and light. Phonons and photons can interact in several different ways, and these interactions form the basis of powerful experimental techniques used by physicists and materials scientists around the world. 2. The most direct interaction is infrared absorption. In ionic crystals, optical phonons create oscillating electric dipoles. An oscillating dipole can absorb electromagnetic radiation at its resonant frequency. For most crystals, optical phonon frequencies fall in the infrared range, typically between 1 and 50 terahertz, corresponding to wavelengths between 6 and 300 micrometers. So when infrared light at the right frequency shines on an ionic crystal, it is absorbed by creating optical phonons. This absorption is very strong. In a frequency range around the optical phonon frequency, ionic crystals are essentially opaque to infrared light. This range is called the Reststrahlen band, German for residual rays, because when broadband infrared is reflected off such a crystal, only certain frequencies outside this band survive. A more subtle interaction is Raman scattering, discovered by C.V. Raman in 1928, for which he received the Nobel Prize. In Raman scattering, a photon of visible light interacts with the crystal and is scattered with a different frequency. The frequency shift equals the frequency of a phonon that was either created or destroyed in the process. If a phonon is created, the scattered photon has lower frequency. This is called Stokes scattering. If a phonon is destroyed, the scattered photon has higher frequency. This is called anti-Stokes scattering. Raman spectroscopy is extraordinarily useful. By measuring the frequency shift of scattered light, you directly measure phonon frequencies. And phonon frequencies are like fingerprints of a material. Different materials, different crystal structures, different compositions all have different phonon frequencies. So Raman spectroscopy can identify materials, determine crystal quality, measure strain, detect defects, probe temperature, and much more. It is non-destructive, requires minimal sample preparation, and can be focused to a spot smaller than a micrometer. It is one of the workhorses of modern materials characterization. There is a related technique called Brillouin scattering, which involves acoustic phonons rather than optical phonons. The frequency shifts in Brillouin scattering are much smaller, but the principle is the same. Brillouin scattering measures the speed of sound in materials and can probe the elastic properties with high precision. It can also study phonon behavior in specific directions, which is useful for characterizing anisotropic materials. An even more exotic phenomenon occurs when optical phonons and photons couple so strongly that you can no longer consider them as separate entities. Near the optical phonon frequency of an ionic crystal, an incoming photon does not simply pass through or get absorbed. Instead, it becomes mixed with the phonon. The quantum of this mixed mode is called a phonon polariton. It is part light, part vibration. Inseparable, the phonon polariton has its own dispersion relation, different from either pure photons or pure phonons. In the polariton picture, there is no absorption per se, only a modification of how light propagates through the material. The light slows down enormously, or speeds up, or even travels backward, depending on the frequency. Phonon polaritons are being actively researched for applications in nanophotonics, where controlling light at the nanoscale requires novel approaches. Let us now venture into the cutting edge of phonon physics, the frontiers where researchers are pushing our understanding and capabilities to entirely new levels. The first frontier is phonon engineering in nanotechnology. When you shrink a material down to the nanoscale, phonon behavior changes in fundamental ways. In a bulk crystal, phonons can have any wavelength from very long all the way down to twice the atomic spacing. But in a thin film that is only 10 nanometers thick, you cannot have phonons with wavelengths much larger than 20 nanometers traveling perpendicular to the film. The phonon modes become confined, quantized by the geometry of the nanostructure. This confinement changes the phonon spectrum, eliminating low-frequency modes that would exist in bulk. The practical consequence is that thermal conductivity is dramatically reduced in nanostructures. With fewer available phonon modes and more boundary scattering, heat has trouble getting through. This is actually desirable for thermoelectric devices, which convert heat to electricity. The efficiency of a thermoelectric device is proportional to a figure of merit called ZT, which increases when thermal conductivity decreases while electrical conductivity remains high. By nanostructuring a material, engineers can scatter phonons while leaving electrons relatively unaffected. This selective scattering is possible because phonons and electrons have different wavelengths and are scattered by different types of features. Researchers have created structures called superlattices, alternating thin layers of different materials that can reduce thermal conductivity to remarkably low values while maintaining good electronic properties. Silicon-germanium superlattices, bismuth telluride nanostructures, and many other nano-engineered materials have achieved thermoelectric performance far beyond what bulk materials can achieve. All of this is phonon engineering, controlling and manipulating phonon transport at the nanoscale. Taking the idea further, researchers have created phononic crystals. These are periodic structures designed to control phonon propagation in ways analogous to how photonic crystals control light. Just as a photonic crystal has frequency ranges where light cannot propagate, a phononic crystal has frequency ranges where phonons cannot propagate. By engineering these structures, you can create thermal barriers that block heat flow at specific frequencies, waveguides that channel phonons along specific paths, and resonators that trap phonons at specific frequencies. Phononic crystals have potential applications in thermal management, vibration isolation, sound insulation, and even information processing. Imagine a computer chip where you can direct heat flow exactly where you want it, keeping sensitive components cool while directing waste heat toward radiators. Or imagine a building material that blocks sound at speech frequencies but allows low-frequency rumble to pass through. These are the possibilities opened by phonon engineering. The second frontier is topological phonons. Topology is a branch of mathematics concerned with properties that do not change under smooth deformations. In physics, topological properties are robust, protected by fundamental symmetries, and cannot be easily destroyed by disorder or imperfections. Over the past 2 decades, physicists have discovered that electrons in certain materials can have topological properties, leading to topological insulators and topological semimetals. These materials have special conducting states on their surfaces that are immune to scattering from defects. Now, physicists have discovered that phonons can have topological properties too. In certain carefully designed crystal structures or metamaterials, the phonon band structure can have topological features. The most exciting consequence is the existence of topological phonon edge states. These are phonon modes that exist only at the surface or edge of a material, travel in only one direction, and cannot be scattered backward by defects or disorder. They are protected by topology. Imagine the applications. A heat conductor where thermal phonons can only travel in one direction, a thermal diode, the phononic equivalent of an electrical diode. Or an acoustic waveguide where sound travels along the edge of a material without any backscattering, regardless of obstacles or imperfections. These ideas are still largely in the research phase, but the theoretical foundations are solid, and early experimental demonstrations have been achieved in acoustic metamaterials. The third frontier is phonons in quantum information science. This is perhaps the most surprising application of phonon physics. For decades, quantum computing research has focused on electromagnetic degrees of freedom, superconducting circuits manipulating microwave photons, or trapped ions manipulated by laser light, or photonic qubits traveling through optical fibers. But in recent years, Phonons have emerged as a new platform for quantum information. The key insight is that mechanical vibrations can be quantum. A single phonon is a quantum of vibration, and like any quantum system, it can exist in superposition states and become entangled with other quantum systems. If you can create, manipulate, and measure single phonons with high fidelity, you have a new kind of qubit, a phononic qubit. Several experimental platforms are being explored. Surface acoustic wave devices use phonons that propagate along the surface of a piezoelectric crystal. These surface phonons can be coupled to superconducting qubits, allowing quantum information to be transferred between electromagnetic and mechanical systems. Optomechanical systems use the radiation pressure of light to couple photons to mechanical vibrations of a tiny membrane or beam. In these systems, single phonons can be created, detected, and entangled with photons. In 2019, a team at the University of Chicago demonstrated quantum entanglement between two phononic modes in separate physical locations. This was a landmark experiment showing that mechanical vibrations can carry quantum information and be entangled just like photons. In subsequent work, researchers have demonstrated quantum error correction using phononic modes, quantum teleportation of phonon states, and other operations required for quantum computing. Why would you want phononic qubits when photonic and electronic qubits already exist? Because phonons have some unique advantages. They are slow, which means they interact with matter for longer periods, making coupling easier. They have short wavelengths, which allows for much more compact devices. And they can couple to many different types of quantum systems, acting as a universal quantum bus connecting disparate quantum technologies. Phonon-based quantum memory is another exciting direction. Because phonons travel slowly and interact strongly with matter, they can store quantum information for relatively long times in mechanical oscillators with very low dissipation. Some researchers envision hybrid quantum systems where information is processed using superconducting circuits and stored using phononic modes. The fourth frontier is one of the most mind-bending applications of phonon physics: analog gravity. General relativity tells us that gravity is the curvature of space-time, and that this curvature affects how everything moves, including light. In extreme cases, like near a black hole, space-time is so curved that not even light can escape from within the event horizon. These ideas are extraordinarily difficult to test directly because we cannot create real black holes in the laboratory. But we can create something analogous. Consider a flowing fluid and sound waves propagating through it. If the fluid is flowing faster than the speed of sound, then phonons emitted in the supersonic region cannot escape upstream. They are trapped, just like light inside a black hole. The boundary where the flow speed equals the sound speed is the acoustic analog of a black hole event horizon. This system is called a dumb hole, or a sonic black hole. These analog systems allow physicists to test predictions about black hole physics in a controlled laboratory environment. One of the most exciting predictions is the analog of Hawking radiation. Stephen Hawking predicted in 1974 that black holes should emit thermal radiation due to quantum effects near the event horizon. This Hawking radiation has never been directly observed from a real black hole because it is unimaginably faint. But the analog prediction for sonic black holes says that a flowing fluid with a sonic horizon should emit thermal phonons from the horizon region. And this has been observed experimentally. In 2016 and subsequent years, Jeff Steinhauer at the Technion in Israel created a flowing Bose-Einstein condensate with a sonic horizon and detected the spontaneous emission of correlated phonon pairs from the horizon. One phonon escapes outward and the other falls inward. The phonon pairs were entangled, confirming a key prediction of Hawking's theory. This is phonon physics at its most profound, using humble sound quanta to probe the deepest questions about quantum gravity. A related phenomenon is the analog Unruh effect. The Unruh effect predicts that an observer accelerating through vacuum should perceive thermal radiation, even though an inertial observer sees nothing. The phonon analog says that an accelerating detector moving through a phonon vacuum should perceive thermal phonons. This prediction connects the physics of sound in crystals to the deepest structure of quantum field theory in curved spacetime. There is another connection between phonons and fundamental physics that deserves mention. The Casimir effect. The standard Casimir effect involves electromagnetic fluctuations in vacuum. Two uncharged, perfectly conducting plates placed very close together in vacuum experience an attractive force. This force arises because the plates restrict the allowed electromagnetic modes between them, reducing the vacuum energy between the plates relative to outside, creating a net force pushing the plates together. A phononic analog of the Casimir effect exists too. If you have two boundaries inside a crystal placed very close together, the allowed phonon modes between them are restricted. This restriction modifies the phonon contribution to the free energy and creates a force between the boundaries. This phononic Casimir effect has been theoretically predicted, and there are efforts to observe it experimentally. It connects the physics of lattice vibrations to the vacuum fluctuations of quantum field theory. Now let us bring this all back down to earth. Let us talk about phonons in your everyday life. You encounter phonon physics every single day, whether you realize it or not. Why does your phone get hot when you use it intensively? Because the electrons flowing through the transistors in the processor are scattering off phonons. Every time an electron scatters, it loses some energy, and that energy goes into creating more phonons. More phonons means higher temperature. Your phone getting hot is literally the conversion of organized electrical energy into disordered phonon energy. Managing this heat is one of the central challenges of modern electronics design. As transistors get smaller and clock speeds get higher, the density of phonon generation increases. Without effective thermal management, which means effective phonon transport away from hotspots, chips would burn themselves out in microseconds. Why does a winter jacket keep you warm? Your body generates heat. That heat must travel through the jacket to escape into the cold air outside. A jacket works by inserting material with poor thermal conductivity between your body and the environment. Down feathers and synthetic fill work because they trap air. Air is a gas with molecules far apart, and phonon-based heat transport is very inefficient in gases because the atoms are not bonded to each other in a lattice. Heat must be carried by air molecules physically moving from one place to another or by radiation. If you eliminate convection by trapping air in small pockets, you have created an excellent thermal barrier. The phonon mean free path in a gas at atmospheric pressure is only about 70 nanometers, and there is no lattice to support coherent phonon propagation. The result is very low thermal conductivity. How does ultrasound medical imaging work? An ultrasound probe sends pulses of high-frequency sound into your body. These sound waves are literally phonons. As the sound travels through tissue, it encounters boundaries between different types of tissue, muscle to fat, fat to organ, organ to fluid. At each boundary, some of the sound reflects back. The reflected sound is detected by the probe, and the time delay tells you how deep the boundary was. By scanning across the body and measuring reflections, the machine builds up an image. The physics of sound reflection at interfaces, the dependence of sound speed on tissue type, the attenuation of sound as it passes through tissue, all of this is phonon physics applied to biology. Seismic waves, the waves generated by earthquakes, are phonons in the earth. P waves are longitudinal acoustic phonons propagating through rock. S waves are transverse acoustic phonons. The speed of these waves depends on the density and elastic properties of the rock they pass through. By measuring how long seismic waves take to travel from an earthquake to detectors at various locations around the world, geophysicists can map the interior of the Earth. They can determine where the crust ends and the mantle begins, where the mantle ends and the outer core begins, and where the outer core ends and the inner core begins. The fact that S waves cannot travel through liquids was the key evidence that Earth's outer core is liquid. All of this is phonon physics applied on a planetary scale. Acoustic metamaterials are engineered structures that manipulate sound in ways impossible with natural materials. They can bend sound around objects, making them acoustically invisible. They can focus sound to points much smaller than the wavelength, enabling super-resolution acoustic imaging. They can create one-way sound channels that transmit in one direction but block the reverse. All of these exploit the physics of phonon propagation in designed periodic and resonant structures. The mathematics is the same as phononic crystals, but the applications range from noise cancellation to medical imaging to underwater communication. Even the phenomenon of thermal expansion, the fact that materials expand when heated, is fundamentally a phonon phenomenon. It arises from the anharmonicity of interatomic bonds. In a perfectly harmonic potential, the average position of an atom would not change regardless of how vigorously it vibrated. But real bonds are anharmonic. They are asymmetric. It is easier to stretch a bond than to compress it by the same amount. So as vibration amplitude increases, the average position of atoms shifts slightly outward. The cumulative effect of all atoms shifting outward is that the material expands. The coefficient of thermal expansion is directly related to the Phonon-Gruneisen parameter, which quantifies how phonon frequencies change with volume. This connects phonons to everyday observations, like bridges expanding in summer and contracting in winter. Let us now take a step back from the technical details and contemplate what phonons teach us about the nature of reality. This is where physics becomes philosophy, and it is beautiful. The most profound lesson of phonons is the concept of emergence. A single atom cannot have a phonon. You need many atoms, arranged in a lattice, vibrating collectively, before the phonon concept even makes sense. The phonon is an emergent phenomenon. It exists at a higher level of description than individual atoms. It is not reducible to any single atom or any single bond. It is a property of the collective, of the system as a whole. In 1972, Philip Anderson, one of the greatest condensed matter physicists who ever lived, wrote a famous essay titled "More is Different." His thesis was that at each level of complexity in nature, new phenomena emerge that cannot be predicted from the properties of the level below. The laws of physics at the atomic level are necessary but not sufficient to predict the emergent phenomena at the collective level. Phonons are a perfect example. You can know everything about a single carbon atom, its mass, its electron configuration, its quantum states, and you still cannot predict the existence of phonons. You need to assemble many carbon atoms into a diamond lattice before phonons emerge, and once they emerge, they obey their own laws, have their own properties, interact in their own ways. They are a new reality that exists only at the collective level. This leads to a deeper question. Are phonons real? What does it mean for something to be real? Phonons are not fundamental particles. They are not listed in the standard model of particle physics alongside quarks, leptons, and gauge bosons. You cannot isolate a phonon and put it in a box. It exists only within a material. It is an excitation of a collective, not a thing in itself. And yet, Phonons carry real energy. Measurable, quantifiable energy. Phonons carry real crystal momentum. They have real, measurable velocities. They interact with real electrons and change real electrical resistance. They enable real superconductivity that can be measured to have truly zero resistance. They can be detected individually in quantum experiments. They can be put in quantum superpositions. They can be entangled. They satisfy all the criteria we usually apply to determine whether something is real. So are they real or not? This is the question of scientific realism. One philosophical position says that only fundamental entities are real, and everything else is just a useful description. In that view, phonons are not real. Only atoms and their motions are real. Phonons are just a mathematical convenience for describing those motions. Another philosophical position says that if something has causal power, if it can produce measurable effects in the world, then it is real regardless of whether it is fundamental. In that view, phonons are absolutely real, because they cause heating, cause resistance, cause superconductivity. I find the second view more compelling. If phonons cause real things to happen in the world, if they carry real energy and can be individually measured and manipulated, then calling them unreal seems like an arbitrary philosophical choice that does not match how we actually use the concept of reality in everyday life and in science. But I acknowledge this is a deep philosophical question without a definitive answer. There is an even deeper level to this. Consider the parallel between phonons and the particles of the Standard Model. In modern quantum field theory, every particle is understood as an excitation of a quantum field. An electron is a quantum excitation of the electron field. A photon is a quantum excitation of the electromagnetic field. A quark is a quantum excitation of the quark field. In exactly the same mathematical language, a phonon is a quantum excitation of the displacement field of the lattice. The mathematics is identical. The formalism is the same. Creation and annihilation operators. Fock space. Number states. Vacuum fluctuations. All the mathematical machinery of quantum field theory applies equally to phonons and to fundamental particles. So why do we call electrons fundamental and phonons emergent? The difference is that we know what phonons are made of. We can see the underlying atoms. We can describe the system in terms of individual atoms if we want, even though that description is much more complicated. For fundamental particles, we have no such underlying description. We do not know if electrons are made of something simpler. As far as we can tell, the electron field is truly fundamental, not emergent from anything below. But some physicists have speculated that perhaps what we call fundamental particles are themselves emergent. Perhaps space-time has a microstructure, analogous to the atomic structure of a crystal. And perhaps particles like electrons and photons are quasi-particles of this space-time microstructure, in the same way that phonons are quasi-particles of a crystal lattice. This is speculative, and we have no experimental evidence for it. But the mathematical parallel between phonons and particles makes this idea at least conceivable. What we can say with certainty is that the same mathematical framework, quantum field theory, describes both the emergent excitations of known systems and the apparently fundamental excitations of nature. This unity of mathematics across such different physical contexts suggests something deep about the structure of reality. Nature seems to use the same patterns, the same mathematical structures, at every level. Whether this is because all levels are truly unified, or because our mathematical frameworks impose this apparent unity, is itself a deep question. Let us now pull all the threads together. We have traveled an enormous distance in this exploration. We started with the familiar phenomenon of sound, the pressure waves that travel through air and let us communicate with each other. We zoomed into solid materials and discovered that at the atomic level, Sound is carried by vibrating atoms connected by spring-like bonds. We learned that these vibrations organize into collective patterns called normal modes, each with a specific frequency and wavelength. Then we brought in quantum mechanics. We discovered that the classical picture fails at low temperatures because it cannot explain why heat capacity drops towards zero. Einstein and Debye showed that vibrational energy must be quantized, just like light energy. Each quantum of vibrational energy is a phonon. The phonon was born from the marriage of lattice dynamics and quantum theory. We explored the properties of phonons in detail: their energy, given by h bar times omega, their crystal momentum, given by h bar times k, their classification into acoustic and optical branches, longitudinal and transverse modes, their statistical nature as bosons, following the Bose-Einstein distribution, their creation by thermal energy, and their destruction by cooling. We discovered that phonons are the carriers of heat in solid materials. Thermal conductivity depends on the heat capacity, velocity, and mean free path of phonons. Diamond's extraordinary thermal conductivity is explained entirely by its phonon properties. The temperature dependence of thermal conductivity reflects the competition between increasing phonon population and increasing phonon-phonon scattering. Umklapp processes provide the fundamental mechanism of thermal resistance in pure crystals. We explored how phonons interact with electrons. They cause electrical resistance by scattering conduction electrons. The more phonons present, the higher the resistance. And in their most spectacular feat, phonons mediate the attractive interaction between electrons that leads to Cooper pair formation and superconductivity. Without phonons, superconductivity in conventional materials would not exist. We saw how phonons interact with light. Infrared absorption occurs when photons excite optical phonons. Raman and Brillouin scattering allow us to measure phonon properties using light. Phonon polaritons arise when the coupling between phonons and photons becomes so strong that they merge into a single hybrid entity. We ventured to the frontiers of modern research. Phonon engineering in nanostructures for thermoelectric devices. Topological phonons with protected edge states for one-way heat transport. Phononic qubits for quantum computing and quantum information. Analog gravity experiments using phonons to simulate black hole physics and Hawking radiation. And we connected phonons to everyday life. The heat in your phone, the warmth of your jacket, ultrasound imaging, earthquake detection, thermal expansion of bridges, all phonon physics. Finally, we contemplated the philosophical implications, the emergence of phonons from collective atomic behavior, the question of what is real, the surprising mathematical parallel between emergent quasiparticles and fundamental particles of nature. The phonon is perhaps the most underrated concept in all of physics. It touches almost everything in materials science, solid-state physics, engineering, nanotechnology, and even quantum information. Without understanding phonons, you cannot understand why metals conduct heat, why insulators insulate, why superconductors superconduct, why your computer generates heat, or how sound travels through the earth. Phonons are everywhere, doing everything, all the time. And yet most people have never even heard the word. I hope this exploration has given you a new appreciation for the quantum nature of sound. The next time you hear music, remember, those sound waves, when they enter a solid material, become quantized into discrete packets of vibrational energy. Phonons, the particles of sound. They are quantum objects living inside every solid thing you have ever touched. They carry the heat that warms you. They create the resistance in your wires. They make superconductivity possible. They are being used to build quantum computers. And they teach us that reality is layered, that new phenomena emerge at every level of complexity. and that the same mathematical beauty pervades every corner of the physical world. That is what a phonon actually is. And that is why sound behaves like a particle. Now let me take you even deeper into some aspects we touched on but did not fully develop. Because the story of phonons has so many facets, so many connections, so many surprises that a single pass through the topic cannot do it justice. Let us revisit and expand on several key areas. Let us go deeper into the mathematics of lattice vibrations, not with equations that would be hard to follow in a video, but with conceptual clarity about what those equations tell us. Consider the simplest possible crystal, a one-dimensional chain of identical atoms, equally spaced, connected by identical springs. This is called a monatomic linear chain. It is a toy model, but it contains all the essential physics. Each atom can move left or right from its equilibrium position. When one atom is displaced, the springs connecting it to its neighbors exert restoring forces. These forces cause the disturbance to propagate along the chain as a wave. The key result from solving the equations of motion for this system is the dispersion relation. For the monatomic linear chain, the angular frequency omega depends on the wave vector k according to omega equals 2 times the square root of k over m times the absolute value of the sine of k times a over 2. Here k is the spring constant, m is the atomic mass, and a is the spacing between atoms. This formula encapsulates profound physics. At long wavelengths, the sine function is approximately linear, so omega is approximately proportional to k. This gives a constant speed of sound, which equals a times the square root of k over m. At short wavelengths, the sine function saturates, and omega reaches a maximum value of 2 times the square root of k over m. This maximum frequency is the highest frequency phonon that can exist in this chain. No amount of external driving can create a lattice vibration above this frequency. It is a hard cutoff imposed by the discrete nature of the lattice. The group velocity of phonons, which determines how fast energy travels, is given by the derivative of omega with respect to k. Near k equals 0, this is the speed of sound, and it is highest. As k increases, the group velocity decreases, reaching 0 at the zone boundary where k equals pi over a. At the zone boundary, the phonon is a standing wave. Energy does not propagate. This is why the phonon spectrum has a natural bandwidth. Low frequency. Long wavelength phonons travel fast and carry heat effectively. High frequency, short wavelength phonons near the zone boundary travel slowly and contribute less to heat transport. Now consider a diatomic linear chain, alternating atoms of 2 different masses, m1 and m2. This introduces optical modes. The dispersion relation now has 2 branches. The lower branch is the acoustic branch, which goes from 0 frequency at k equals 0 up to some maximum. The upper branch is the optical branch, which has a minimum frequency above 0 and a maximum frequency. At k equals 0, the acoustic mode has all atoms moving together, while the optical mode has the 2 types of atoms moving in opposite directions at a definite frequency, even at infinitely long wavelengths. The gap between the acoustic and optical branches is important. At frequencies within this gap, no phonon modes exist. The crystal cannot vibrate at these frequencies. This is the phononic band gap of the bulk crystal. The width of the gap depends on the mass ratio. The more different the 2 masses are, the wider the gap. If the masses are equal, the gap closes, and you recover the monatomic chain result. Extending to 3 dimensions and real crystals makes the picture much more complex, but the principles remain the same. Real crystals can have many atoms per unit cell. Each adds 3 branches to the phonon spectrum. A crystal with n atoms per unit cell has 3n phonon branches, 3 acoustic branches, and 3n -3 optical branches. A complex material like silicon has 2 atoms per unit cell, giving 6 branches total. A material like yttrium barium copper oxide, the famous high-temperature superconductor, has 13 atoms per unit cell, giving 39 phonon branches. The phonon spectrum becomes enormously complex, but the fundamental concepts remain intact. The phonon spectrum of a real material is measured experimentally using a technique called inelastic neutron scattering. Neutrons are ideal probes for phonons because they have no electrical charge. Their masses are comparable to atomic masses, and their de Broglie wavelengths at thermal energies are comparable to intraatomic spacings. When a neutron scatters off a crystal and creates or destroys a phonon, the neutron loses or gains both energy and momentum. By measuring the change in energy and direction of the scattered neutron, you determine the energy and wave vector of the phonon. Mapping out all the measured phonon energies as a function of wave vector gives you the complete phonon dispersion relation. Inelastic neutron scattering experiments require intense neutron sources, which typically means nuclear reactors or spallation sources. These are large-scale scientific facilities. Oak Ridge National Laboratory in the United States, the Institut Lau Langevin in France, and the Japan Proton Accelerator Research Complex are among the world's leading facilities for measuring phonon dispersions. The measurements require sophisticated instruments called triple-axis spectrometers or time-of-flight spectrometers, and the experiments can take days or weeks to map out the full phonon structure of a material. An alternative technique is inelastic X-ray scattering, which uses very high-energy X-rays from synchrotron sources. X-rays have the advantage of penetrating deeply into materials and working with very small samples. The energy resolution needed is extremely demanding because the phonon energies are tiny compared to the X-ray photon energy. It is like trying to detect a millimeter change in the length of something that is a kilometer long. But modern synchrotron facilities achieve this through remarkable instrumentation. Let me now go deeper into the thermal properties of phonons, because there are fascinating details we have not yet covered. One important concept is the phonon density of states. This is a function that tells you how many phonon modes exist at each frequency. In the dB model, the density of states increases as frequency squared, up to the dB cutoff frequency, where it drops to 0. In real materials, the density of states is much more complex. It has peaks, valleys, and features called Van Hove singularities, where the density of states has abrupt changes. These features arise from the detailed shape of the phonon dispersion curves and have observable consequences in the heat capacity and thermal conductivity of materials. The phonon density of states directly determines the heat capacity. At very low temperatures, only the lowest frequency phonon modes are excited. Since the density of states goes as frequency squared at low frequencies, and the energy per mode is proportional to frequency, the heat capacity at low temperatures turns out to be proportional to T cubed. This is the Debye T cubed law, one of the great successes of phonon theory. It has been confirmed experimentally in countless materials and is one of the most well-established predictions in all of solid-state physics. At temperatures above the Debye temperature, all phonon modes are fully excited, and the heat capacity reaches the classical Dulong-Petit limit of 3 kb per atom. Between these two limits, the heat capacity varies in a material-specific way determined by the detailed phonon density of states. Something interesting happens in low-dimensional systems. In one-dimensional and two-dimensional systems, the density of states at low frequencies behaves differently from 3 dimensions. In one dimension, the density of states is constant at low frequencies. In 2 dimensions, it is linear. This leads to different temperature dependencies of the heat capacity. Linear in T for one-dimensional systems and quadratic in T for two-dimensional systems. These predictions have been verified in materials that are effectively low-dimensional, such as carbon nanotubes and graphene. Graphene, a single layer of carbon atoms, shows a T² heat capacity at low temperatures instead of T³, confirming its two-dimensional phonon physics. Let us also discuss in more detail the concept of phonon mean free path and its implications. In a very pure crystal at low temperatures, the phonon mean free path can become enormous. In very pure silicon below about 10 Kelvin, phonon mean free paths of several millimeters have been measured. In isotopically purified diamond at similar temperatures, mean free paths of centimeters are possible. At these scales, phonons travel ballistically, like particles in a vacuum, bouncing off the crystal surfaces rather than scattering off each other or off impurities. In the ballistic regime, heat transport is qualitatively different from the diffusive regime we are used to. In normal heat conduction, the thermal conductivity is a property of the material and does not depend on the size of the sample. In ballistic heat conduction, the thermal conductance depends on the size and shape of the sample, because it is limited by how many phonon modes can carry heat through a given cross-section and how they reflect off boundaries. This is analogous to the difference between a gas flowing through a wide pipe and a gas flowing through a pipe narrower than the molecular mean free path. There is even a regime between ballistic and diffusive called the hydrodynamic regime, where phonon-phonon normal processes are frequent, but umclap processes are rare. In this regime, the phonon gas behaves like a fluid. It can exhibit phenomena analogous to viscous flow, second sound, and even phonon-Poiseuille flow. Second sound has been observed in a few materials at low temperatures, including helium-4, bismuth, and sodium fluoride. It is a dramatic demonstration that phonons collectively behave like a flowing fluid under certain conditions. Let me explain second sound more carefully, because it is a truly remarkable phenomenon. In ordinary thermal diffusion, if you create a hotspot on one end of a material, the heat spreads out gradually, like dye dissolving in water. There is no wave-like propagation. The temperature profile just smooths out over time. But in the hydrodynamic regime, temperature disturbances do not diffuse. They propagate as waves. If you create a pulse of heat at one end, it travels to the other end as a coherent pulse, arriving at a well-defined time. This is second sound. The speed of second sound is related to the speed of ordinary sound, but is typically smaller by a factor of the square root of 3 in isotropic materials. Second sound was first predicted by Lev Landau in 1941 for superfluid helium, and was observed experimentally in 1944. In solids, it was first observed in bismuth at 3 to 4 Kelvin by researchers in 1966. The conditions for observing second sound are very restrictive. You need normal processes to be frequent, but umclap processes to be rare. This typically requires very pure crystals at specific temperature ranges. In recent years, there has been renewed interest in hydrodynamic phonon transport because of its potential relevance to nanoscale heat management. In very thin graphite samples, which are quasi-two-dimensional, hydrodynamic phonon transport has been observed at temperatures as high as 100 Kelvin, much more accessible than the extremely low temperatures required in bulk crystals. This is because graphite has an unusual phonon spectrum with very different properties in plane versus out of plane, creating conditions favorable for hydrodynamics. Now let me expand on the role of phonons in one of the most technologically important fields today: semiconductor physics and electronics. Every semiconductor device, from transistors in your computer to LEDs to solar cells, is affected by phonon physics in profound ways. In a semiconductor, electrons can be in either the valence band or the conduction band. The gap between these bands determines the semiconductor's properties. Photons with energy equal to the band gap can excite electrons from valence to conduction band, which is how solar cells and photodetectors work. But here is where phonons come in. In silicon, the most important semiconductor of all, the minimum of the conduction band and the maximum of the valence band occur at different points in the Brillouin zone. Silicon is an indirect band gap semiconductor. This means an electron cannot make the transition from valence band to conduction band by absorbing a photon alone, because the photon provides energy, but essentially zero momentum. The momentum difference must be provided by a phonon. So in silicon, light absorption and light emission require the simultaneous participation of both a photon and a phonon. A photon provides the energy, and a phonon provides the momentum. These phonon-assisted transitions are much less probable than direct transitions, which is why silicon is a poor light emitter and why silicon solar cells have lower absorption coefficients than direct gap materials like gallium arsenide. The entire photovoltaics industry is shaped by this phonon-related fact. Silicon solar cells must be thick to absorb sunlight effectively, while gallium arsenide cells can be thin. The difference is whether phonons need to participate in the absorption process. Phonons also play a central role in the process by which hot electrons cool down in semiconductors. When an electron is excited high into the conduction band, it has excess kinetic energy. It loses this energy by emitting phonons, cascading down through energy states while creating a shower of phonons. This process is called thermalization, and it happens on a timescale of about 1 picosecond. The emitted phonons are typically longitudinal optical phonons because the electron-phonon coupling for these modes is strongest in polar semiconductors. This rapid thermalization is actually a major source of efficiency loss in solar cells. When a high-energy photon is absorbed, the excited electron quickly loses its excess energy to phonons, which becomes waste heat. Only the energy equal to the band gap can be converted to useful electricity. If we could slow down phonon emission and extract the hot electrons before they thermalize, solar cell efficiency could be dramatically improved. This concept is called the hot carrier solar cell, and it is an active area of research. The challenge is controlling phonon dynamics at the nanoscale to prevent or slow thermalization. Let us now go deeper into the physics of thermal interface resistance, which is critically important in electronics cooling. When heat flows from one material to another, there is always a thermal resistance at the interface, even if the two materials are in perfect atomic contact. This is called Kapitsa resistance, after the Russian physicist Pyotr Kapitsa, who first observed it at the interface between helium and a solid in 1941. The origin of Kapitsa resistance is the mismatch in phonon properties between the two materials. If material A has a very different phonon spectrum from material B, then phonons traveling in material A cannot easily continue into material B. They reflect back at the interface. The probability of transmission depends on the match between the phonon densities of states and sound velocities on both sides. The more different the materials, the higher the interface resistance. The simplest model for this is the acoustic mismatch model, which treats phonons like waves hitting an interface between two media with different acoustic impedances. Phonons transmit according to rules analogous to how electromagnetic waves transmit at an interface between media with different refractive indices. The reflection coefficient depends on the ratio of acoustic impedances. In practice, interfaces are never perfectly smooth and abrupt. There are interdiffusion layers, surface roughness, adsorbed atoms, oxide layers, and other complexities. A more realistic model is the diffuse mismatch model, which assumes all phonons are scattered randomly at the interface, and the transmission probability depends only on the density of available states on each side. Thermal interface resistance matters enormously in modern electronics. A microprocessor chip might have heat generated in a silicon layer that must pass through multiple interfaces before reaching the cooling system. Each interface adds thermal resistance. At the nanoscale in advanced chip architectures, with layers only a few nanometers thick, the interface resistance can dominate over the bulk thermal resistance of the layers themselves. Understanding and minimizing phonon scattering at interfaces is a critical challenge for the semiconductor industry. Let me now discuss some other fascinating manifestations of phonons in materials. Thermal expansion, as I mentioned earlier, arises from the anharmonicity of interatomic potentials. But let me be more precise about how this works. In a perfectly harmonic crystal, the equilibrium positions of atoms do not change with temperature. Atoms vibrate more vigorously at higher temperatures, but remain centered at the same positions. There is no thermal expansion. Real crystals are not perfectly harmonic. The potential energy has cubic and higher order terms. These anharmonic terms mean that the restoring force is not perfectly proportional to displacement. Specifically, most bonds are asymmetric. They are harder to compress than to stretch. This means that as vibration amplitude increases, the average position of each atom shifts slightly outward, toward larger separations from its neighbors. Each atom shifts a tiny amount, but the cumulative effect across the entire crystal is measurable expansion.